Okay. Okay, everyone, welcome. Welcome to today's Learn Live session. My name is Matt Sigler. I am the Executive Director for ICC's Plumbing, Mechanical, and Fuel Gas Division, or PMG team. Part of what the PMG team focuses on, besides providing technical support and training to our members and industry stakeholders, is consistently looking into the latest research, innovations, and best practices throughout the world to further strengthen our existing codes and standards portfolio. Today, I have the honor of introducing you to Dr. Esper Andiroglu, who ICC has been working with him and his team at the University of Miami for the past 3 years in addressing water scarcity, efficiency, reuse, and resource management, along with on-site wastewater treatment, as we look to develop new industry solutions. Dr. Andiroglu has both a bachelor's and master's degree in mechanical engineering and a PhD in civil and architectural engineering. At the University of Miami, he is a professor of practice with a primary appointment in the Department of Civil and Architectural Engineering and secondary appointments in the Department of Chemical, Environmental, and Materials Engineering and at the School of Architecture. He is a registered professional engineer and a LEED AP accredited educator who has extensive industry experience in evaluation, design, operation, performance, analysis of systems in the built environments, including those centered around sustainability, preservation and recovery of energy and water resources, and transformation of design and construction practices through innovation. So if you would please, join me in welcoming Dr. Andiroglu as he shares with you some of the university's findings through their partnership with ICC.
Thank you very much, Matt, for that kind introduction, and a pleasure sharing this hour with all of you and sharing our work. So, I will jump right in by also stating that this is a really topic that we're passionately engaged in, and we are it's a team effort. Myself, within my lab, and team of researchers who are pursuing their PhD degrees are passionately engaged in this work, and we do really feel that it is a much needed focus area, and hopefully will end up delivering highly valuable outcome beneficial to global communities. Are we able to share our screen, Drew? Great. So, World Water Awareness, this month, actually, we have a lot to talk about on this topic. And today, again, we're going to highlight just a few of these areas. So water resource management, water quality and its implications to public health and safe management of water resources. And of course, talking about water scarcity doesn't really come without addressing conservation and efficiency. Let's switch to the next slide. So, as I mentioned, SURREAL Sustainability and Resilience Adaptation Laboratory is a laboratory housed within the Department of Civil Architectural Engineering at University of Miami, which myself and my team heavily engaged in. Leading the efforts of SURREAL Lab is primarily focused on really looking at applied research coupled with fundamental research, and how can we translate such research outcomes into deployed innovative solutions benefiting global communities and society. And along the way, of course, public education and training the adequate workforce in meeting those needs is also our mission. Let's go to the next. So I want to quickly highlight the 3 significant team members who are going to be sharing their work this afternoon with us, who are really passionately engaged in this topic. So first, Ms. Kyra Williams, who is a second year PhD student. Her focus primarily resides around integrating various water conservation provisions into applied solutions, and thus delivering a response to better water resource management practices. Followed by Mr. Drew Rich, who is in his last year of PhD work and is producing really exciting results on accurate water demand estimation framework, development of such framework, all with the intent of improving water use efficiencies within the built environment. And last but not least, Mr. Austin Perry, who is engaged in developing standards for on-site wastewater treatment and management standards, which can help aid us in operationalizing water reuse practices and safe management of wastewater within the regulatory frameworks aligned with regional policies and incentives. So with that said, let's go on. Next slide. So what is water scarcity? Really, you see two definitions on the screen when you look here. And by no means, water scarcity definition is limited to just these two definitions. But the top one, in my mind anyway, it really speaks to supporting the global population's health and well-being through the nutritional needs and in order to sustain life and enjoy. So therefore, it's focused on public health and well-being, really. And the second one is same mission, but yet kind of touches on the balancing act of supply and demand, and with various environmental factors which might impact water quality and thus result in, let's say, reduction of available safe use of water streams, or population growth, which continues to increase in the recent decades. How do we maintain that balance, that we are meeting the needs of the growing population while delivering healthy lifestyles and nutritional needs for the population? So again, these are just two definitions, or my interpretation of these two definitions, but we could describe it in many other ways. What we want to highlight here is that water scarcity is a serious topic, and it is becoming more and more significant because of various environmental hazards, and therefore we hope we'll all take it to heart and see how we can overcome, or we can better manage. Let's go on to the next slide. So I already mentioned this, as I was talking about the scarcity definition. So if you look on this slide that you're looking at right now, you can pretty much see all the different sectors water is used for. So energy production, irrigation, where those crops and agricultural products are benefited, industrial uses, and domestic, where potable water uses that we're most familiar with every day. So if you look at the population growth, the trend of population growth and the increasing demand, it is anticipated that by 2050, which is not that far, 25 years from now, but 40 to 50% of global population will be experiencing water scarcity challenges. Today, a good significant percentage of that same population is already experiencing it. So again, this hopefully highlights that through those, when you see those red curves, for example, the way they're intersecting, that supply versus demand interaction becomes highlighted. So therefore, efficient management of available resources is really essential. Let's go on to the next slide. It's also important to highlight that, water is a resource that we often take for granted, but very small percentage of total water available on Earth is actually readily accessible and usable by us. And, the three categories, the primary categories, the agricultural being 70%, industrial 22%, and residential premise plumbing systems use around 8%, makes up most of that demand. But all of that comes out of about 2.5% of total water available on Earth that is fresh water. The remaining 97.5% is salt water. But out of that 2.5%, bulk of that is really embodied within frozen icebergs. So the readily available, water for us on the surface is right around 0.3 to 0.5% of the total available water supply. So readily accessible, meaning, yes, we do have earth layers, water table, but again, that requires energy and additional resources for direct access. So therefore, water that is readily available, how well we manage it and how efficiently we utilize it is really significant. So let's move on to the next. So if we were to, with all that said, hopefully we all recognize that we must really arrive at certain strategies that help reduce our water consumption and better utilization of this precious resource. So to better describe this intent, we can think of it as putting this into two categories. On one side on the left, as you see, end use reductions, and where you can improve the efficiency. You can bring on regulatory guidelines that help guide the end users, and better education, awareness of this better management need and practices. Where on the right side, water reuse, again, is having that access to the very small percentage of readily available water. How can we better manage that water? What are the reuse practices? So that really speaks, we can categorize it into the three categories in general. One, I'm going to start from the bottom, protecting water resources from the water quality. The more protection we are implementing, the less environmental pollution we're introducing, the more readily available these water resources become for reuse, because they reduce the treatment burden, which that have significant cost implications. So on-site wastewater treatment technologies and management standards, which you're going to hear a lot more about, from my team in a little bit, are certainly key in helping that shape up. And then creating alternate water supply streams, really, for use through the reclamation of already used water. And again, you're going to hear a lot more about that. So with that, I'm going to turn over the discussion to my team member, Kyra Williams, who's going to exemplify some of the provisions that can be integrated that can actually help operationalize or help you visualize some of the benefits, the pathways that can come from these, whether it's end use reductions or water reuse practices. How can we operationalize them? So Kyra, go ahead.
Thank you, Professor Ndaroglu. So by understanding the various pathways, the mission to create a standardized approach that could further be applicable to all cities was created by the International Code Council, the ICC, through development of the 2021 International Water Conservation Code provisions, which I'll continuously refer to them as the IWCCP. Next slide, please. So as a part of our research, our focus is establishing how can we conserve water and in communities within the various different types of building typologies, ranging from single-family homes, multifamily, and as well as commercial properties. So within the 4 cities that you see listed here on the screen, we focus on Las Vegas, Phoenix, Houston, and Des Moines. And we've managed to do remarkable work in understanding how a city's geographical location actually can aid or hinder this task. So next slide. Phase 1, we decided to focus on single family homes. We obtained the average unit size, how many bedrooms, the average square feet. And next slide. And we also, for phase 2A, focus on multifamily. So being that multifamily construction is actually very vast in nature, we broke it up into different buildings within it. So we focus on garden style low-rise, mid-rise, as well as high-rise properties, and obtained an average dwelling unit size of 875 square feet and what the typical bedroom, bathroom would look like. Next slide, please. So moving forward, in order to assess the outcomes of in-use reductions as well as water reuse, we decided to focus on the IWCCP's measures and how they could be implemented. So as shown, there are several measures here that are listed. I'll state them: the water efficient fixtures and appliances, gray water systems, rainwater harvesting, HVAC condensation recovery, hot water systems and piping, alternative water resources, plumbing system design, and landscape irrigation efficiency. But for our research and for our studies, we decided to focus on the quote unquote low-hanging fruit, which are the 4 that are circled in blue. Next slide, please. And as a result, we decided to focus on the benefits that these 4 can actually give us, which is, of course, lower water consumption, but also lower energy consumption as well. And also looking at the different multiple uses that can actually come from the implementation of these measures, such as the multiple uses for a consumer for their everyday life, such as laundry, gardening, washing your car, but also looking at it from the city standpoint of reducing the water demand and also limiting stormwater runoff. Next slide. So as a result, after performing numerical modeling and forecasting models, we evaluated the impact of these 4 measures within each of the 4 cities. But today I'll look at Houston. So focusing on the Houston single-family residences, in the top left corner, we forecasted the amount of new single-family construction homes based on the current trend, and also did an upper and lower bound to figure out if it was to go up higher, what it would look like. And in the chart to the right, we focus on the projected aggregate total of conserved water using these measures for newly constructed homes, as well as the implementation of 5% of retrofitted existing homes. So each measure is stacked in order to show the impact of each of these specific measures in correlation to each other. And in the lower left-hand corner, the chart to the lower right-hand corner, we decided to combine the forecast for new single-family construction, as well as 1% of retrofitted existing homes, as well as 5% of retrofitted existing homes, to compare the aggregate totals of water conserved over the next 6 years. So as a result, the numbers that you see circled in blue, just for existing homes alone, 15.67 billion gallons of water is basically projected for an annual potential aggregate total for using these measures. However, we also wanted to look at new and existing. So if we're just looking at new homes, 23 billion gallons of water can be conserved. Now, if we decide to, we also decided to perform a cost analysis as to understand what the cost would be to implement each of these specific measures. And for instance, for fixtures alone, a one-time cost is $254. Whereas if we're focusing on implementing a rainwater or condensation system, it'll be $339. And Further, if we were to focus on gray water harvesting, it'll be $483, which would just all be a one-time cost that that existing homeowners would have to just absorb. Next slide. So after applying the same framework, we also apply this to the multifamily construction. So within that, if you can just flip back to the first slide and flip back to this one again. If you're able to see, if you're able to see the difference, the comparison of data of the implementation of fixtures versus a single family or multifamily, you can already see a difference just based off of the building typology. So for instance, for a garden style home in Houston, for existing homes, 21.1 billion gallons can be conserved. Next slide. So our overall takeaway was that there's not a one size fit all approach. It is actually very vast, where different measures are actually not, each measure cannot work for every building typology. So if we're looking at the garden, mid-rise, and high-rise, you can see on the screen from 559 billion gallons to 14 billion gallons. Even though you may implement these measures, they may not all fit. But for the city of Houston, it should pop up. There we go. For the city of Houston, 698 billion gallons are projected to be the approximate total potential aggregate for water conservation for multifamily construction. Next slide, please. So comparing the data between phase 1 and phase 2, at the top, you see your new multifamily construction, and at the bottom, you'll see your new homes. So if you're able to look and using your deductive reasoning, you're able to see that the implementation of water efficient fixtures is super paramount, regardless of the city. Specifically, if we're looking at Las Vegas, for instance, it definitely helps and it aids in conserving water. Versus if you're looking at Des Moines or Houston, when you're looking at rainwater, it is not the same. When you're looking at multifamily construction, it may not be of a big benefit, but it does help compared to single family, where it is a tremendous benefit that is actually very helpful and something that you should implement. Whereas if you look at Phoenix, which is the last column, rainwater may not be of major assistance, and there may need to be more focus on implementation of water efficient fixtures and gray water harvesting. Next slide, please. So to do a quick deep dive into the analysis of potable versus non-potable water, the graph shown to the left shows how much water is consumed in blue, and in green, the implementation of water efficient fixtures. As you can tell, even just with the implementation of water efficient fixtures, that doesn't meet the potable demand. However, if we decide to look at the non-potable graph to the right, you have consumption in the very bright blue, I'll say teal, and then you have the rainwater and gray water harvesting, which are respective to each other within the graphs. If you're using non-potable demand for rainwater and gray water for each of the cities, it may or may not actually meet the non-potable demand. For instance, Houston, since that's what we're focusing on today, the implementation of rainwater harvesting and gray water harvesting can meet the non-potable demand. And if you were to use the rainwater, gray water, and the water efficient fixtures in order to meet the total water consumption, it will meet the total demand. Whereas if you're looking at Las Vegas, rainwater and gray water harvesting may not meet the full non-potable demand, but with the help of water efficient fixtures, it'll be able to meet the total water consumption needs for that specific city. So with that being said, if we were to combine these measures, ultimately the goal is to find out where the synergy is and where there's a certain level of a combination of an approach to water conservation that can ultimately be beneficial for all. And further, I'd like to go ahead and introduce my colleague, Mr. Drew Rich, who will continue discussing holistic solutions.
Thank you so much, Kyra. And yeah, so what Kyra was talking about earlier is really great, right? It talks about what could be, right? And that's very important. But in order to get there, we've got a long way to go. And that's kind of where the research that we're doing comes in with the Surreal Laboratory. So I want you guys to take a moment and look at this graph right here. So we're looking at the overall water supply, and it's essentially called withdrawals by use category. If you look and pay very close attention to the bottom graph, you're going to see a little purple bar, right? And my research primarily focuses on that purple bar. So that is public supply. So that means every day we use water for showering, we use it for consuming, cooking, all of these things, irrigation. But notice that with the introduction of a lot of water efficient practices, things such as it's called the EPA Act. It's intended to reduce the amount of water consumption in residential buildings. We've noticed that this purple bar, which used to be growing at a linear rate or increasing every year, has started to slow in growth or stop. So why does that matter, right? When we look at this, we have to consider something called premise plumbing systems. These are our buildings. These are our the portion of the building that delivers potable water to the end user. So whenever we take a shower, our potable water systems are kind of supplying that water so that you can do that. Whenever you go to cook pasta, whenever whatever you want to do in your home, we have a supply system that's delivering that water. Now, how does this connect to water efficient practices, right? So why is this a challenge? What does this even mean? Well, if you think about it, when we design our systems, we design them in a tree-like manner, right? And if we suddenly reduce the amount of water in the system, but we don't change the overall consumption, like the sizing of these systems, we have an issue. We have something that's leading to what's called stagnation, or where the water in the pipe is staying there for long periods of time. All right, so I'll talk about it a little bit, but in order to understand this, we're going to talk about supply system design a little bit. So first, like I said, they are formed in a tree-like structure. So you can see in A, we have that tree-like structure. It's a distribution system. And we have one main distribution line that feeds all of the rest of the apartments or units or single-family homes, whatever you want to consider, right? So example in point B, we distribute water from the main supply, and then subsequent points kind of distribute that water to the units or single-family homes. Now, pipe sizes are based on the concept of simultaneous usage, right? So instead of sizing them so that all of the fixtures can be active at once, we size them so that we can reduce the amount of usage, right? So the question I always ask people is, how many times in the past year have all of the fixtures in your house been on? Your shower was running, your toilet was on, your kitchen sink was on, your lavatory. And when you think about it like that, it's very unlikely. So that's why we design to the most probable fixtures being on at the same time. So we design to what's called simultaneous usage, which ones are likely to be on at the same time. Now, when we get into that, we run into some problems, right? So when we're designing a system, we know that there's a range of flows that the pipe can experience, right? For example, not all of your fixtures are on at the same time throughout the day. So when we look at this, we have to select an appropriate design flow rate. Now, what happens, because again, there's a distribution, let's say. There's likely ranges that the pipe can access. So for example, for a pipe that has all of the fixtures like a shower, a water closet, a lavatory, there's an expected amount of flow that's going to be going through that, and we have to size to that design, right? So what happens if we end up undersizing, or we pick a design flow rate to select the pipe size that's much less than we expect it to be? Well, we have some significant issues. First of all, we have increased pressure losses that result in user dissatisfaction. We have increased velocities that may result in premature failure of components, right? So we don't want to undersize it because that would lead to some pretty bad things. But what happens on the other side? What happens if we oversize these systems? Well, we start to see that there's an increased capital cost, right? If you're using a 3-inch pipe versus a 2-inch pipe, that costs more, right? We see health risks from opportunistic pathogens, things like Legionella. So if the water is sitting in that pipe too long, it can develop a lot of pathogens that can actually negatively impact the end user, right? We have inefficient energy use from pumps. So if we expect to pump 100 gallons of water and we're only pumping 20, we've now picked a pump that's way too big for the distribution system. And then we also have excess water stored. So that's increasing the amount of water that you have to treat and maintain, which also increases cost, right? So it's very important to select that kind of middle ground and get the design flow rate for these systems correct, right? So that's the why. What is the gap? And we see since the 1980s that there's been significant reductions in the way we use water. The only problem is we haven't changed the design framework, right? So Kyra talked a lot about efficient water use practices, right? That's great, that's fantastic. But what's happened is we haven't changed the way we size our systems. So we have significantly oversized pipes. This sometimes even 100% oversized. So this can lead to some of the problems that I was discussing in the previous slide. And we really, really want to avoid that. So what are the solutions, right? Right now, there's a major research gap, right? So this is the problem. And again, this is a little bit of a complex side, but what we're seeing is that there's a gap in the research. We need to be able to accurately understand or create a methodology that can predict the appropriate amount of water flowing through a pipe so that we can then size the pipes appropriately and avoid all of these negative consequences, right? So we see here where the red line is that's pointed up, and you can see it kind of right here, that we have the current design selection where the actual flow rate over here is significantly decreased, right? So we're trying to avoid that. So what is our solution? We want to make something that first is resilient. So we wanted a global product. We wanted to make this a living document so that we didn't end up in a situation where we needed to do this exact same process in 10, 20, 30 years, right? So as Kyra said, we're always implementing new strategies to try and save water. If we create a system that's not going to be updatable, we're going to end up in a situation that we have to go back and do this process all again. On top of that, we wanted to have a simplified design approach, right? So engineers are ultimately going to be the people using these systems. So we need to make sure that this is simple enough and efficient that they can use it without, getting turned off from it being too complicated. In terms of the public health and safety, we want to make sure that this is meeting the needs of the building environment, making sure we're not having any pathogens in our system. So really making sure we accurately size those pipes. And then we want to make sure that this system is modular and adjustable, right? So like Kyra had said, based on different cities, there's different requirements for water saving practices, right? Some places are more water efficient than others. So we want to make sure that this product that we develop or this idea is going to be modular and adjustable, right? It can adapt to the location of where we're trying to design the system. And in essence, that is the goal of the ICC 815 committee, who's tasked with developing this standard. Now, what we've ended up developing is a new pipe sizing approach through our research that allows for all of this to occur, right? So we've developed a pipe sizing system that uses a network or a series of lines and nodes that we can automatically provide a simple design approach for the entire building. Now, what does that mean? Why is this important, right? Because again, all these fancy graphs, these fancy distributions, they're great, but what is the actual benefit of having these? So if we look down below, we can start to see that this provides a simple design approach, right? Very simple, very easy to use. This is a self-improving algorithm, right? So it allows us to automatically update this as soon as we get new information and data about water consumption patterns. This adapts to the communities around the world, right? So if we take data from the US, we can make a system for the US. If we take data from the UK, we can make a system for the UK. We can do this as long as we have the appropriate data dictating how water is used. And on top of this, this goes through and it saves a lot, right? It saves time, it saves money, it saves materials, it saves energy. It allows us to more accurately design our systems and reduce waste that we really don't need to have, right? So when we look at these efficient practices, we want to make sure we make solutions that can adapt to the changes that we're making in order to combat water scarcity. So from an efficiency standpoint, that's one of the solutions we produced. So moving on to the next, which we talked about water reuse, I briefly want to go over it. I know Kyra kind of covered it, but I think it's important to retouch on this. So what is water reuse and what are some of the streams? As Kyra mentioned earlier, we have streams called black water reuse, industrial reuse, rainwater and atmospheric, condensate, gray water, and each one of these has a different water quality, right? So when we talk about reuse, this can be a challenge, right? We can't treat gray water, which is water from sinks, from dishwash, from laundry, showers. We can't treat that the same as we treat our toilet water, right? It doesn't make sense. Those are very, very different types of water, so they require different water, treatment levels, right? And that's a challenge, right? That's one of the things that's standing in the way from implementing something like Kyra's suggestion. On top of that, there's a lot of different uses, right? We don't necessarily need to treat the water that we're irrigating to the same level we need to treat the water that we're drinking to. right? So in order to kind of relay this issue, I kind of want to talk about a case study. So what you're seeing here is a map. This map is the United States and all of the different legislative strategies that the US employs, right? It's very fragmented. And the point of this graph isn't to understand what these strategies are, it's to show that they are indeed fragmented. There's a lot of inconsistencies on how states deal with water reuse, right? So I'm going to move on because this is where it gets a little bit more complex. Now, each one of these has their own legislative system, but they also have their own permitted uses. So we're going to look at the permitted uses in terms of their overarching categories, right? So within each one of these bins, like our potable reuse, we have secondary. We have potable reuse direct, and then we have indirect. Irrigation, we have irrigation of crops for human consumption and irrigation of crops for non-human consumption. And you can see over here that each one of these has a category. Also notice that each one of these categories has a different number of states that allow it. And each one of those has a very complex, it's very hard to determine what's acceptable nationwide. Now, this is a challenge. Let's go even further. So inside each of these categories, like the ICHC, we have even more categories, right? So we have things like when we're talking about irrigation, we have athletic fields, we have cemeteries, we have college and university campuses, commercial campuses, golf courses. All of these have different standards for the acceptable treatment levels, right? So it makes it very, very challenging to actually implement these water reuse strategies like Kyra's talking about. And that's kind of the key takeaway I want you to take from these slides is that it makes it almost a barrier for implementation of these strategies. So through our research, what we've been able to do is we've been able to work with ICC to develop a new version of what we call the IPC Chapter 13 or IPC 1301 and 1302, where this is responding to that challenge, right? So with ICC in a very large, great working group, it was a pleasure working with them, it was awesome. We were able to essentially take all of these different water use categories and then associate them with tiers, right? So we see down below, we have 4 tiers. And based on those tiers, we can then simplify the and create a holistic guidance on what uses are permitted and then allow for authorities having jurisdiction to be really able to enforce these and be able to say, okay, that makes sense, this is permitted, right? So we're taking that first step in allowing water reuse practices to truly be implemented. Now, the next step we have to consider, and Austin, my colleague, is going to be talking about, is what it has to happen in terms of from a wastewater side, and what are the different types of wastewater systems that can actually allow these to be implemented. So from there, I'll hand it over to Austin Perry.
Thanks, Drew. You're gonna have to click on that.
Yeah.
Okay. So hi, everybody. I'm Austin. I'll be talking today about some of the core challenges as far as residential wastewater management relates to water reuse, some water scarcity resilience, and we'll just go through kind of a global perspective on what's all going on out there. Where can we make some inroads to facilitate more water reuse, and where we might find some challenges and some obstacles to implementation and adoption across the world. So first things first, some of the core challenges in residential wastewater management. The first one is community-centered sanitation solutions. So what I mean by this is we've got to focus on solutions that are locally appropriate and they're driven by the community needs. One of the things that we run into quite consistently are manufacturers or producers of these types of systems who might say, you know, every year we go and we do some philanthropic work wherever on planet Earth where they may not have sanitation systems. And we take our systems that we make and develop and we bring it over there and we give it to them. And then we expect them to use it indefinitely. And we're going to take them from potentially open defecation or some low-level pit latrine type system to some advanced water management type system. And they ask us, you know, like, what is your perspective on that? Do you think, you know, we've left this project a year ago in our minds, it's still working and it's working great. What do you think? And we ask some basic questions about the types of the communities that they drop this system off in, and in about 2 or 3 questions, they start to realize, you know what, maybe that system wasn't the perfect system for that area. It's doubtful it's still in use. The parts are probably sold off, et cetera, et cetera. So what I mean by that is it might be great for us, you know, in our perspective, from like an American perspective or whatever it is, to say, hey, you know, we all use septic, we're all capable of using some advanced wastewater solutions. But just because we can doesn't mean we can copy and paste to someplace else on planet Earth and expect the exact same outcome. That is not how it works. And that is arguably one of the greatest obstacles we have to overcome, is getting past what we think should be getting done and talking to the community. What do you all want? What do you all think you need? Answering those questions can give us a much better understanding of what this community is capable of managing. And in finding that solution, we can set them on a pathway to say, okay, here's where you are now. Here's what you're going to be working on. In the future, in order to accomplish water reuse, potable water reuse or any type, these are the steps you're going to need to take. These are the obstacles you're going to have to overcome. We can't get you there right now, but if you start down this pathway and start knocking out some of these obstacles, you'll get there eventually. So that's kind of what we're going to be talking about as far as community center sanitation solutions. And then in addition to that, the strategic investment and implementation. So you need to address not only the technical capacity, can this built system physically pull this off? Can it technically pull this off? Most of the time you'll hear the answer is, yeah, perfect working in order and perfect working conditions. This system will treat the wastewater to a very high standard and you're all set. Except that's not necessarily how the real world works. You're going to have to address the need for, you know, financial constraints. Does this cost a lot of money? Does this place have money? You're going to need to talk about the human capital. If something breaks, is this something I can fix? All I have is my cell phone. I can go on YouTube. I can look up the answer on YouTube. Oh no, I need a professional, you know, service person to come and fix this. I can't do it myself. Okay, that's a little different capacity building. And then, of course, you know, your governance with the ICC. Not only do we want to do this, but we have to kind of understand what it is we're doing. And if we do it wrong, we can create more problems than we're solving. So we view the standards, the building codes, as far as on-site wastewater treatment, as that guiding light. It may not be completely applicable to everybody right now, but if we set it up in such a way to where people understand where they are, where they're trying to go, and all of the milestones and checkpoints along the way, we can set them off on their own pace. And eventually, over a long enough period of time, they'll ultimately get to their end goal, which is, again, whatever specifically they might need. Next slide, please. And then we have the last one is the international objectives and priorities. I'll just quickly touch on that. Essentially, just going back to saying, you know, we have the international community might have its one set of goals. We want to turn our wastewater into potable drinking water. That is, you know, the dream that everyone is kind of working towards. However, what you'll find is there are many, many communities on planet Earth that do not want that. They just culturally or socially, they understand that it's wastewater. They understand that it's icky. They understand that there's some sort of health impact associated with it. And they understand that you can treat it. You can treat it to potable reuse. You put it under a microscope and everything's clean, but still they know what it was at one point. And because they know that, they're put off by the idea of drinking it later. There are some hoops you have to jump through. There are some considerations you have to kind of acknowledge and address. And then maybe they'll consider it. But if you're simply going to every community on planet Earth and saying we're doing potable water or wastewater reuse, you're going to see some pushback in some areas. So it's an interesting kind of obstacle to overcome. So we have our international priorities, potable water reuse, and we have those local priorities, those local needs, which say, hey, you know, that's great, but that's not for us. You know, we need something a little bit different, and we'll be 2 thumbs up about it. So on this slide, what we want to do is empower communities for those global health improvements. Since we're talking about wastewater, we know that this is a public health challenge. If we're able to satisfy the sanitation and the public health challenges associated with sanitation, a lot of indirect benefits are seen. And this is everything from workforce participation to education participation, et cetera, et cetera. So we have a complex challenge of wastewater and sanitation. Essentially, what you're looking for is it's not just the technical capacity. There's the human element, there's the materials element, there's the governance and education element. All of these types of forms of capital all come into play. And depending on where you are, they all might show themselves a little bit differently. They're there in principle, but they might manifest themselves a little bit differently. And you kind of got to know what those all are so that when they manifest themselves, you kind of recognize, oh, this is just this one thing. Oh, okay, yeah, I've seen this before. We can manage with this. So empowering communities is resilience. So it's not only important to simply give somebody a wastewater system and say, off you go. You know, here's what you've been missing, and now everything's fixed. What you want to do is say, okay, this is something that you really need to do. Sanitation is critically important to all of your developmental goals. If you solve this, you can create a better upward trajectory in your developmental progress. So what we want to do is say, okay, community, you need to understand where you are, you need to understand where you're going, and take it upon yourself, have a little bit of agency to kind of help yourself along to get there. So what we want to do is say, here you are, here's where you're going, and here are the steps you need to take. Off you go. Let's see how you do. So what we want to do is create that pathway forward. In order for that pathway forward to be identified and described and communicated to other people, you know, we have to have a set hierarchy of some sort that says, this is where you are, this is your next step, here's a further step, another step, on and on. The idea being, no matter where you are, you see the entire pathway, the entire sanitation development pathway laid out before you. Because at some point in your developmental progress, you might sit there and say, hey, we need to make a pivot. You know, the pathway we're on right now is a good one, but we need to pivot away from it because of A, B, and C reasons. Okay, if we need to pivot, what can we pivot to? This pathway should demonstrate, should show them, should communicate to them options, viable options for where they are, some minor incremental improvement to get to that next step. And then from there, you know, they're free to go to the next step, to the next node, as they see fit. And what we keep hearing is meet people where they are. You know, don't make assumptions about them. Don't say you have to do this and then ultimately you'll get to where you're going. No, hey, where are you in your developmental progress right now? We'll meet you there and we'll get you started on a more better trajectory for developing your sanitation infrastructure. Next slide, please. And you're just going to click through. So some of the international efforts that you might see as far as just common wastewater treatment systems out there. Of course, most people might be familiar with septic. That is kind of the most common as far as like America, Canada, Europe, Australia, that type of area. Septic systems are very, very common. However, there are other systems out there that are in use to some wide degree. You know, I'm not here to talk about some things that 20 or 30 people are experimenting in a lab with. This is stuff that is currently in use all over planet Earth. So we have everything from, you know, top left, like an incineration toilet. Below that, we have our vermin composting, so using animals to help digest and degrade waste. That is one avenue of approach. In the top right, we have our modular design systems. So these are things that you would see post-disaster, things getting dropped off, these kind of TEUs, these containers getting dropped off so people can use them, the toilets, the showers, et cetera, et cetera. The one I want to point out is the center left. The center left machine that is hard to, what is this that we're looking at? So this is the International Space Station's water recovery system. Now, if you think of the International Space Station, you're like, that's not necessarily a house per se, but it is how you could think of a multi-family housing structure in a very hostile environment. And they need to have their life support systems. They need to have everything that we need down here. They just do it a little bit differently. So this is advertised as a $9 million toilet, and it is about 99% efficient at recycling liquid waste into potable water. So urine into water. So this is one of those things where if you said, you know, Austin, what are we all building towards? What's the best thing we can go and get? I'd say if you had $9 or $10 million, this is one of those things that you might want to look into. Now, when I say $9 or $10 million, I hope everyone goes, you know, I don't know that that's perfect for me in my home. I get that I can treat to a very high level, but I don't know that that's for me. And you're probably right. You're probably with the vast majority of planet Earth that we cannot afford this. The International Space Station is the most expensive machine ever built. So this is one of those very specific items built for such a specific task. So our international efforts and proposed solutions range from simple to complex. They range from something that an individual can do, like that center right. This is what you call a cat hole, like if you're a backpacker. to multifamily, where maybe several households live in a high density area, don't have enough land space to have a septic system individually. So they pool their resources to find something that's affordable for them, that's useful for them, and that can fit in their within their constraints. And then distribute and decentralize. This is often used interchangeably. However, there's some efforts to kind of say, hey, look, one of them is a decentralized system where you are in control of all of the maintenance, all the operations, et cetera, versus a distributed system, which is you have hired a contractor to come and manage this for you. And what we want to do is move away from wastewater as a hazard and push it as fast as we can to a resource. We want to make sure that nothing goes to waste, and that whatever we do put in our wastewater, that is something that we can use as an input for literally anything else. Anything that we can use it for would be a win. Next slide, Drew. All right, and so very quickly, some of those resources, if you could just click through, some of those resource constraints and adoption barriers, how I said, hey, look, we can technically pull this off, but there are some resource constraints, and that's your capital in all forms. That's your, do they need to be educated on this system? Do they have the proper governance? Do they know what needs to be enforced? Do they know what somebody is looking for to confirm that this is potable water reuse? Do you have those standards involved? And then do you have the workforce? If there's anything that comes up, are you the workforce, or do we have to hire the workforce? Does it have to be a professional workforce or a skilled workforce? Can it be my Uncle Joey? You know, we have to have all these types of answers, because the types of systems we need to select are based on what our capacity is. And if we don't have the capacity for it and we select that system's not going to last, and it's probably going to fail very quickly. So in one kind of perspective, maybe we're not trying to hit home runs. We're not trying to provide the most advanced wastewater treatment system solution to all of planet Earth. Maybe we're just trying to put people on a path to where they can make incremental improvements over a long enough period of time, again, to get where they need to be going. Drew, next slide, please. And then, of course, you have to consider your local environment. If you want to create, I want to use a potable water reuse system and I'm going to rely on septic systems. Okay, that's perfect. Maybe you don't want to do that here in Miami, where the water tables are rising, septics are inefficient. Maybe that's not the pathway you want to go down. So all of these types of environmental hazards all have their all contribute to certain types of constraints that will factor in to what types of wastewater systems you want to select. And with those environmental considerations in mind, maybe those are what determines whether or not you can have potable water reuse versus water for irrigation versus water for industry, or whatever it might be. Drew, next slide. And this is where we come up with WISE. So WISE is the toolkit and the framework that we're using to kind of quantify, to identify and understand what those major capital constraints are. And as far as wastewater treatment systems are concerned, we've narrowed it down to these 6 understandings. Now, these 6 understandings each have 3 levels, as you can imagine. Something like resource availability. There's a difference between me looking around my desk and finding the things I need versus me having to go out and buy something from Amazon versus me having to find that one manufacturer on planet Earth to create or design or build this one filter or whatever it is I need. So there's levels to all of this, and these are the 6 major constraints that we're looking at. If all of these are satisfied, you have a good shot at making sure that the wastewater system you selected will last for a very long time. If these gates aren't satisfied, what you're going to see is failures start to occur, and not only does that wastewater system become damaged, stop treating, or ultimately fail, but you'll have that second and third order effects where not only is it not great, it's actually an obstacle to the rest of the community. So when you look at, hey, what are those social constraints? These are the 6 that you're going to want to look for and satisfy. Drew, next slide. So water reuse and how we go about selecting the appropriate system for the appropriate person in the appropriate place. What you're going to have to remember to consider are the adaptation strategies. Where you are, you might have to change your approach if you're in the middle of the desert versus on an island versus in the high Alps of Switzerland or something like that. They all have their own different constraints, and you're just going to have to identify them and work with them. So maybe it's water reuse, maybe it's something for irrigation, and you can consider that a water reuse win. The community, if there's people involved, The people have to be on board with this because they are the first and major obstacle to success. And awareness, what is the system? How does it work? How can I ruin this? And how can I avoid ruining this? All of that knowledge needs to be there. Or the first chance they get, they're putting something in a toilet that shouldn't be there, and then the entire system is destroyed. The regulatory compliance, and this is what we're working with the ICC to kind of create that pathway to say, this is where you are. Here are the standards that you need to create a good wastewater system. Here are all the other steps that you can take. And here are all the standards and building codes associated with that to achieve the things that you want to achieve. And then innovative solutions. We need to figure out, innovative solutions might work here, but what are the innovative solutions going to do someplace else on planet Earth? Are they still workable, or are they just going to fail outright because they're lacking some of that capacity within those gates? So these are all the things that I've been looking at and working on to try and say, once we have our standards and building codes for that water reuse, how do we translate that from a piece of paper onto deployment across planet Earth? And with that, I'll toss it back to Dr. Andrew, who's going to bring us on home.
Well, thank you very much, Austin, Kyra, and Drew, for summing all this up for us. And hopefully, in a short, hour duration, we were able to highlight the relevance and significance of water scarcity challenges and safe management of water reuse, water resources, so that we are able to sustain healthy lifestyles for not only for today, but for generations to come, years from now, here on Earth. So again, we hope that you are able to take away some of the key points that we emphasize. Again, summarizing it quickly: water efficiency, various conservation provisions and practices, the path forward for battling water scarcity through efficient management and proper integration and implementation of water reuse practices. And of course, along the way, recognizing that none of this can happen safely and efficiently, effectively, without community buy-in and without broader education, awareness, and establishment of regulatory framework, codes, and standards that ensures that all these steps are done in a safe manner for public health and well-being. So with that, if you do have any questions or would like to go and know a little bit more in depth about any of these topics, feel free to reach out to us. Our information is readily available through this site, and we would be happy to share much more with you, not only through direct communication, but we will also be hosting a number of other seminars, webinars, in-person conferences in the months ahead, and we welcome and invite you to attend some of those to know more about these topics. Thank you very much for the opportunity to share today.
Thank you very much for joining us this afternoon, and we hope to see you on the next one. Have a great day, everyone.